Our universe, a vast expanse of stars, planets, and galaxies, started from a single point. Imagine something smaller than an atom containing all the energy and matter we see today. About 13.8 billion years ago, this point exploded in an event we call the Big Bang. The universe expanded rapidly, cooling as it went. This cooling allowed energy to convert into particles, forming the building blocks of matter. Gravity began to pull these particles together, forming massive clouds of gas and dust called nebulae. Deep within these nebulae, gravity continued to compress the material, raising temperatures and pressures to unimaginable levels. Eventually, the core of these collapsing clouds became so hot and dense that nuclear fusion ignited, marking the birth of stars. These early stars were like giant furnaces, fusing hydrogen atoms into helium and releasing enormous amounts of energy. This energy lit up the universe, creating the first sources of light after the Big Bang. But stars have a life cycle, and some of the most massive ones end their lives in spectacular explosions called supernovae. Supernovae are some of the most powerful events in the universe. They scatter the heavy elements forged in the star's core far and wide. These elements, like carbon, oxygen, and iron, are essential for building planets and even life itself. Without supernovae, our own solar system and the life it sustains would not exist. About 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, a nebula began to collapse. This particular nebula was enriched with the remnants of countless supernovae, seeding it with the ingredients for a future solar system. As the nebula collapsed, it began to spin faster and faster, forming a disk of gas and dust around a central, growing protostar, our Sun. Within this swirling disk, particles of dust collided and stuck together, gradually growing larger. Over millions of years, these clumps of dust became planetesimals, the building blocks of planets. Closer to the Sun, where temperatures were scorching, only rocky materials like iron and silicates could condense. These materials formed the inner terrestrial planets Mercury, Venus, Earth, and Mars. Farther out, beyond the frost line, temperatures were cold enough for ices like water, methane, and ammonia to remain solid. These ices, along with rock and metal, formed the cores of the giant planets, Jupiter, Saturn, Uranus, and Neptune. These gas giants are behemoths with thick atmospheres composed mostly of hydrogen and helium. The formation of our solar system was a chaotic dance of gravity, collisions, and accretion. Planetesimals crashed into each other, some shattering into pieces, others merging to grow larger. This process continued for millions of years, eventually sculpting the familiar planets and moons we see today. But the story of Earth was far from over. It was about to embark on its own journey of transformation, shaping the very landscapes and environments that would one day support life. In its infancy, Earth was a hot, molten ball of rock, constantly bombarded by asteroids and comets. This early bombardment played a crucial role in shaping our planet. The impacts delivered water and other volatile compounds to Earth's surface, forming the early oceans. One particularly significant impact is thought to have led to the formation of our moon. As Earth cooled, a solid crust formed on its surface. But beneath this crust, the planet's interior remained molten, churning with heat from radioactive decay. This internal heat engine drove plate tectonics, a process that continues to shape our planet today. Earth's crust is broken into several large plates that move slowly over the mantle. Where plates collide, mountains rise, volcanoes erupt, and earthquakes tremble. Where plates pull apart, new crust is formed at mid-ocean ridges. This constant dance of the plates has created the continents and oceans we know today. And it continues to shape Earth's surface over millions of years. But Earth's transformation wasn't just driven by internal forces. The planet's surface was also sculpted by external forces like weathering and erosion. Wind, rain, ice, and even living organisms slowly break down rocks, carving canyons, shaping coastlines, and transporting sediments across vast distances. These geological processes, both internal and external, have worked together over billions of years to create the diverse and ever-changing landscapes we see today. The early Earth was a harsh and unforgiving place. Volcanoes spewed toxic gases into the atmosphere, and the oceans were acidic and hot. Yet in this seemingly inhospitable environment, life emerged. The exact details of how life arose from non-living matter remain a mystery. But scientists believe that in the primordial soup of early Earth, a remarkable transformation took place. Simple organic molecules, the building blocks of life, formed spontaneously from inorganic matter. These molecules, through a process called chemical evolution, gradually assembled into more complex structures, eventually leading to the formation of self-replicating molecules, the precursors to DNA and RNA. The first life forms were simple, single-celled organisms similar to bacteria and archaea. These early microbes thrived in the extreme environments of early Earth, some even harnessing energy from volcanic vents or relying on chemosynthesis rather than photosynthesis. Over time, evolution led to the development of photosynthesis, a process by which organisms could use sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. This oxygenation of the atmosphere was a pivotal moment in Earth's history. It paved the way for the evolution of more complex life forms, including eukaryotes, organisms with cells that have a nucleus and other membrane-bound organelles. From these humble beginnings, life continued to diversify and evolve, eventually giving rise to the incredible array of plants, animals, fungi, and other organisms that inhabit our planet